GM everyone. I'm Yosef or Thomas on Topology and Topology Protocol, which is the what we'll be working on moving forward. And as we may know, past 3 years we've been making a series of game experimentations. But long story short, we've recognized various limitations about blockchains, and so therefore we are trying to improve upon those limitations by conceiving of the new kinds of peer-to-peer network on top of which you can deploy decentralized programs that work differently than smart contracts, but they have different affordances. And we hope that these affordances may help you make better games. So that's the long story short of Topology Protocol.
Okay, so the first talk will be about our journeys in the past 3 years, the various games and experimentations we did that led up to our realizations about the fundamental limits about blockchains and how we want to do about that. Cool. So founding vision of Topology has been to build sovereign, persistent, interoperable realities on the internet. The first experiment that we did, this was in 2022 summer, was Isaac. And Isaac was the three-body problem fully on-chain game running on Starknet. The idea is that, who here have read this three-body problem story, the original story? Wonderful, and there's a Netflix movies coming out, which I think has an interesting choice in actors for like diversity inclusion, but I think it's a good story captured by the film, which is very difficult. I think most of the time, movie adaptation of stories are difficult to make it right. But the idea is that we can have a game about global coordination to avert crisis. And crisis here means that all the players are living on the same planet that is situated in a three-sun solar system, a tri-solar system, and all the players win or lose together. And the players will lose if their planets crash into one of the suns. So the idea is that the players should work together to steer their planets away from the suns for as long as possible. So here we can see that this civilization lasts for 574 blocks after the genesis of their civ. And here's the last snapshot of their civilization before extinction. So you have a tiny dot sitting on the red sun, that's civilization extinction. And how we did this was to run numerical simulations in the Cairo VM that runs on Starknet. So the idea is that every block on Starknet serves as a tick in time that takes the simulation forward, that simulates the dynamics of these celestial bodies and the planet revolving around one another, and they're constrained by, obviously, the gravitational field. And the way players can work together is to play this mini factorial game that we took a lot of inspiration on Factorial and like Zachtronic studio games. So you would play the game by making pipelines of machineries that harvest resources and produce equipment. And ultimately, you'll produce what's called a nuclear rocket. And this rocket will basically be mounted on the ground and push the planet in the reverse direction when launched. So players can basically coordinate about where to put these rockets and when to launch it to steer their planets away from the suns. I think the complexity here is pretty high. One problem about global coordination is that it's really hard for players in different time zones to coordinate. And so a lot of players were, during the game tests, were coordinating on Discord. And ultimately, the fun part is on Discord, where people banter and talk about how to work together. The game is just a visualization of their work. And then we move on to Mumu. So the idea is that blockchains have TPS problems, and there's like a blockchain trilemma, which says if you want high TPS chain, you will be probably sacrificing on some core principles that the autonomous anonymous is sick for in the first place. So we shouldn't be sacrificing those principles. So assuming a blockchain that can't run very fast, what kind of game mechanics can work well despite the slowness? So the idea is that, okay, we can make an asynchronous gameplay where we take TPS out of the question of the game experience. So you play the game locally, you submit your result or outcome to the blockchain at the end of your game session, and that has downstream implications in ranking and matchmaking and so on, but the gameplay is local. So Mumu was a alchemy / chemical synthesis game where assume a worldview where emojis can synthesize into one another. And your job is to program little robots that transport these emojis around the board and deploy formulas so that they merge into other emojis. And at the end of the day, you want to produce the fire emojis, which is energy, as many as possible given a time limit. Right? So we have a board situation, and you have these little robots symbolized by little hands, and they can grab emojis, they can move around and deposit emojis at different places, and you would have color stripes symbolizing the formulas. So when the right emojis are placed at the input of the formula, you will get the formulas gets activated automatically, and you will get the produce at the output. Okay, so we have a circuit building game in short, coated in emoji production game. And I think this website actually still works. This is the front end of the app where you can still play the game. Then we move on to Shoshin because we were fascinated by fighting games. So we thought maybe it's possible to make a fighting games, but it's a synchronous fighting game that works on chain. And it's strange because fighting games are quick twitch games. But we said we have TPS problems with blockchain, so how do we make it work? We make it work by having turning fighting game into an asynchronous game, where instead of playing the game quick twitch with your muscles, you play the game by designing strategies. And strategies is like visual coding. The way we make the API is basically a state machines where you have conditions and actions. So when conditions are met, the actions are executed. And then we have a lot of mechanics wrap around it so that you can have compound conditions, you can invert the conditions, and you can have mix-ups. So in the first layer, you will have a 50% chance of doing the first action, which is a dash backward, and 50% chance of doing a low kick, which is another action, just to have your decision, just have your agent behavior be less predictable to the other side. And you can make arbitrarily many layers, which obviously agent behavior grows proportional to the layers of your decision tree. And there's various gameplays recorded. I managed to harvest some. So you have a taunt there for like a few frames. If you notice that it's a croissant taunt. And if you look at just look at the bar, the HP bar obviously is the red bar. The green bar is the rage bar. So the idea is that you will start with a low rage at the beginning of the game. Your rage grow when you perform aggression, and you can spend 50 rage out of 100 rage for a special move. A special move gives you invincible frames and outstanding damage, but it also has some cooldown frames that you're vulnerable. So it's always a trade-off when to use that. And for defense, there's dashing. And you will notice that dashing gives you invincible frames. So while you're dashing, you're invincible. Attacks doesn't register on your hitbox. And obviously, this entire game loop is programmed in the Cairo contract. So frame by frame, the Cairo contract simulates the decision made by each agent and calculate the hitbox positions, calculate the physics among these hitboxes according to gravity and friction and so on, and then calculate HP changes and rate changes and so on. There are various canceling mechanics. So there are a lot of fighting game players here, I assume. Canceling mechanics basically allows you to fast transition to other action if you cancel at the right frames, which is a way to perform combos. And here is a video that demonstrates that you have a block action, and the way we program our physics makes it so that when you're blocking someone, you get nudged backward a little bit. So there's all these little nuances that we program into the contracts to make the game look, I think, realistic and similar to the fighting game mechanics that players are familiar with. And here this was a fight at the Stanford live playtest that we did at a Stanford blockchain conference last year. Made a Stanford church pixelized in this background. And you can see that the ultimate move was blocked multiple times, dodged multiple times by the dashing frames. So that's what's interesting. And they switched sides because of the jump and so on. But it was great. I think in-person playtest was great. It was much more fun than remote playtest because we had a hotel bar rented and we had big screens projecting the games, and players watching their agents fight. It was great. At the end of our design process, we wanted to tackle, Hadokens, because that allows more expressive fighting styles. But I think we kind of stopped the game development right there. This was the last idea that we did. This is a King of the Hill game. So, okay, we have a core fighting game mechanics, but how do we want to introduce progression, right? Because once you put your agents on chain, you want to have a sense of progression, finding what other people, gaining points, gaining achievements, and so on. And so the idea is that, okay, we have attacker and defenders. Defenders deploy, let's say, 5 agents in a row. If I want to attack at a defender, I will submit one agent that fights their 5 agents in a row. And I need to have non-zero HP at the end to win, right? So this basically tackles the overfitting problem, because agents that are submitted from the defender side on chain is transparent. So I can backtest these behaviors off chain and find a winning strategy. But when there are sufficiently many defender agents on chain, it becomes a much harder fitting problem. And so your agent it's less viable for you to overfit your agent and have trivial hacks. So that was a way to avoid overfitting. Other ways include introducing some kind of deterministic randomness and so on and so forth. But we managed to, we didn't pursue this idea because I think the problems of blockchains were so pronounced to us that we want to tackle the problems. So, okay, so what is the problem? The blockchain problem is the trilemma, right? So we have chains that are proud for their decentralization and their security, but they have problem with scalability, right? And you have other chains that are choosing different edges of these triangle, different trade-offs. But I think all of us here want to stick to the bottom two, decentralization and security. And we work with the scalability, but finding game mechanics that somehow work with the scalability property of the blockchain. Now, can we do better than that? Scalable thesis, right? So we have modular thesis on the left, and on the right is the optimistic superchain, optimism superchain. The idea is that, okay, single threads are slow, but we can shard by applications and have applications run on different application threads that settle their traces on the state of their parent thread. And so applications begin to run in parallel, and they may be able to cross-chain message layer 2 or layer 3 and so on, so that there's some sense of composability remains. The ideas, the problems that we want to point out for this approach is that for an application running on an application thread, it's still a single thread. And a single thread can only do so much, especially when you're running a single thread over a decentralized network where nodes are trying to reach consensus over the internet. That really poses an upper bound on really how fast you can coordinate over the internet, and how fast, therefore, your single thread can take forward. So we discovered CRDTs with the help of Jun Yoon, a good friend from Cosmos ecosystem. There was a long line of research starting from operational transform. So this was late 1990s, early 2000s, where the web users were enamored by being able to collaborate on documents on the web. And there was the Writerly app acquired by Google 2006, and we have Google Doc. Circa 2009, 2010, we have Google Doc where multiple players can collaborate on the same documents over the web. And it was a magical piece of technology. The idea is that you would have multiple users entering characters into the same document, and you want to resolve conflicts so that you would, if users are seeing different versions of a document, then the application would have failed, right? Consistency is the foundation for collaboration. So we need consistency. Now, operational transform has problems with their security when you want to have more nuanced insertion logic and deletion logic, and you want to support more complex data types. And so Google Wave project was a project circa 2010. The idea is that why don't we bring Google Sheet, Google Slides, Google Doc all together and have this ultimate Google platform where everyone can co-work with everyone else collaboratively over the web. The project was discontinued. It used operational transform, and it was just too intractable to make a platform out of. And so there were approaches, if you look into the literature, 2006, there were approaches to propose collaborative document without operational transform. The keyword is WOOT. So literally, there were works that are anti-operational transform or without operational transform. All these work crystallized into what's called CRDTs, or conflict-free replicated data types. We like to call these data types multiplayer data types. So these data types are data types of variables that have built-in strategies for people to concurrently modify and access them. So therefore, we call them multiplayer data types. And the crux of that is conflict-free. So when there's a conflict, we don't want to stop these users and ask them to manually resolve their conflicts, because that will slow down the operation. We want the variable to somehow get automatically replicated to multiple users, and all these users are editing these variables at the same time. And we still want consistency to guarantee, meaning that when users stop editing, after some network delay, everyone will be seeing the exact same value. So we want the consistency to be guaranteed by the data structure itself. So the developers, on top of the data type abstraction, do not have to worry about consistency problems. CRDTs are in production. There are various geo-distributed database solutions using CRDT actually on the back end. Redis, for example, Apple Notes apparently uses CRDTs for their synchronization. And Atom, the code editor, uses CRDT for the tail type function. OrbitDB is a database solution built on top of the Merkle CRDT, which is a work produced by, jointly produced by Protocol Labs and Hayas Network. And Jupyter Lab, for those of you working on data science problems collaboratively over the Jupyter Notebook web interface, it uses CRDT for collaborative coding. Here's a website that documents various real-world implementations of CRDT. So we've seen a lot of collaborative document editing. So our hypothesis is, well, document itself is a world. So why don't we just explode its dimension from a document to a multiplayer world? So this was implemented via YJS, which is an open source a CRDT library in JavaScript. The idea is that we can represent the game state as in CRDT. Players interact with the same game world CRDT at their local speed, so at 30 frames per second or 60 frames per second. And because of the CRDT properties, everyone is guaranteed to see the exact same view after some network delay. So that's the negligible, non-negligible factor in this whole equation about making applications on the web is the speed at which information transmits is non-negligible. And then we did collision handling, because what is an interesting world without implications or interactions among characters? Right, so we implemented collision handling, collision detection, and resolution logic also in CRDTs. It was a very stupid solution. What we did is we have a separate CRDTs representing mailboxes for each actors, and we have intersection detection. And when I detect intersection with you, I will pop a message to your mailbox saying, hey, you should back off by how much, so that we can resolve our collision. And obviously, it has a lot of attack vectors, have gameable collision problems, but nevertheless, we have a prototype working. So then the idea is that, okay, CRDTs can be made for complex game physics multiplayer worlds. So why don't we generalize from here and say, let's make CRDTs available as an add-on for making decentralized applications. And obviously, this runs so fast compared to blockchains, and so this doesn't. The blockchain trilemma it's not applicable to this model. But then, where this model doesn't really overpower blockchains in the sense that, which I'll be covering in the next talk, that the double spending problem is not going to be protected in this model. But you're sacrificing some ordering guarantees that blockchains give you. But as a result, what you gain is you have lock-free asynchronous operations that can go as fast as the local clients want to go. So topology protocol in a nutshell, which I'll be covering in more details in the next talk. It basically provides you with BFT CRDT actors running over peer-to-peer network. And these actors, the network functions like a RAM for the work computer. So there's the notion of ephemerality. There's the notion of closeness to compute, just like the RAM are close to CPU, so they can afford fast access timing, fast compute. And we imagine this protocol to basically complement the existing blockchain protocols and how we all understand how the world computer works. So this is not to replace any blockchain or overpower any blockchain. This is not a blockchain, but this is a P2P network underlying that exposes the programmable objects that are different from smart contracts. And we believe this should complement blockchains and complement smart contracts. Hi. And I think there's quite a lot of information, so I think it's a good idea to have a 3-minute break. And the next time we'll go into the technical details.
Can we play the video again?
Yeah, sure. We'll be starting now with the technical details of our current conception of the protocol. And of course, there's still a long list of open research problems that need to be solved, like any complex distributed systems. But this is our current best conception of how the protocol can work and should work. So I want to cover some prerequisite material first. There's some mental model level departure from how the blockchain works. So I think it may be helpful to cover the prerequisite first. So let's revisit how a typical programmable blockchain works, right? So the fundamental component of a blockchain probably should start with a Byzantine consensus, right? So the consensus problem is that we don't want centralized authority servers to mediate interactions of internet actors or users of the internet. So let's have a peer-to-peer network where users are equal and they have equal responsibilities. Now, without an authority and without a centralized server, it's actually a tricky business to determine what's right and what's wrong. Because then the idea is that everything is relative to everything else. And in this chaos of relativity, how do you determine truth? And I think as we're making games, or in the term of autonomous worlds, or we're making inter-objective realities or inter-objectivity, it's important to specify in programs a notion of truth. And that truth holds between subjects. So it's between subjects, therefore inter, but it's true, therefore objectivity. And we want to have truth, but in a peer-to-peer network, how should we do that? So the Byzantine consensus basically say, okay, we have all these users on the internet, and some may go bad, and some may behave badly. How do we maintain a notion of consensus? Meaning, how can we agree on some truth or some information? Bitcoin uses proof of CPU power. So the idea is that the more CPU power you have, the more vote you have in determining the truth of a blockchain, Bitcoin blockchain. In proof-of-stake chains such as Ethereum or Tendermint, it depends on how much capital stake you have in the system that gives you the proportional power and responsibility to determine truth or to write history to the blockchain. That's a proof-of-stake blockchain. And we all know that there's a myriad of consensus protocols and algorithms in the last decade, right? On the fundamental level, or how the mechanics work at the transaction level, is that we want to run a single thread of transactions that are non-overlapping. And we want to have a total order over all these transactions that are agreed upon by everyone in the system. And then these contracts call one another in cross-contract calls. The problem with this is that essentially, this is what's called strict serializability model, which means that we want total ordering of events or happenings, and we want these happenings to be non-overlapping to one another. So that gives you strict serializability, or I think in plain language, we can just call it single thread operation. Single thread operation gives us Turing complete smart contracts, and we've been playing with smart contracts for almost a decade now. It's 2024. Ethereum was started in 2014. The problem with that is coordination, right? Coordination basically is nodes on the internet trying to coordinate and find what is true, or what information should go into the history of blockchain. And that coordination takes a long time. So for example, if you look at the Ethereum block time of 12 seconds, 99% of that block time is basically nodes trying to reach consensus on the blockchain. Less than 1% is about execution, right? And compare this to a typical affordance that video game developers work with. They don't need consensus. Typically, most of the challenge basically comes in how much compute you can mash into a single game tick or a single frame, and to optimize those computations. But on the blockchain side, we have been assuming that decentralization is costly and consensus takes a long time, and we're trying to design around these affordances. I think one mental model that's useful here is blockchain basically gives you absolute space-time, right? So the idea of absolute space-time is that we have a notion of absolute space. We know that there is the global space that everyone agrees on and can act in. And there's a notion of absolute time, or God's time, or angelic time, that is true everywhere else uniformly in the universe, and that everything or every happening or event can be timestamped by this God time or this angelic time. And when everything can be timestamped by the single time, everything can be ordered on the same timeline. Now, absolute space-time got us all the Newtonian physics and the wonderful aircrafts and spaceship and so on. But on the internet, we're not so lucky, because the speed of light, or the speed at which information transmits, is not very fast compared to how applications run. So this is a seminal paper by Leslie Lamport, 1978. The idea is that there's a strange philosophical circular dependency here, which says, okay, time is an artificial construct, and time should come from ordering of events. But then we're also saying, hey, we're using time to timestamp events. So who determines what? Is time determining the order of events, or is the ordering of events determining time? Right? That's a very strange thing. So Leslie Lamport basically said, okay, let's forget about machine clocks and the notion of absolute time. Let's stick to event orderings. And if we have the orderings, we can derive time from there. But let's not assume we have a time in the first place. And that's basically what gives us ordering events in a distributed system, and so on and so forth. And blockchain basically built on top of this by running a decentralized timestamp service, which is the original Bitcoin blockchain. So timestamping, right? Bitcoin blockchain is a decentralized timestamping network of servers. It allows actors, Byzantine or not, to decide to agree on a single total order of happenings. But this is costly. So the holy grail here is, can we skip coordination? Like the Ethereum block time has 99% spent on consensus. Can we just skip that? And what's the implication of skipping that? Can we still make useful programs on top of a distributed systems where there's no consensus process whatsoever? But if we can do that, then we have lock-free asynchrony, which means that users of this programmable system, distributed system, can progress at their own local speed, asynchronously, not waiting or coordinating or waiting for confirmations or acknowledgement from other people to progress. That gives you lock-free asynchrony. And if we can also have BFT, then we can make decentralized applications out of this system. And that, I think, is the holy grail. Another mental model, since we're departing from the Newton view, will be to think about special relativity. So the special relativity idea is that the truth of the universe, or the state of the universe, is a question of where you're observing from. Right? So the Newtonian spacetime basically says, wherever you're observing from the universe, you basically get the same answer. It's the absolute truth. There's a theological element to that, but special relativity tells us that, okay, if you have a train situation where a light bulb is turned on in the middle of the train section, and the light should reach both ends of the train after some duration. Now, does the light reach both ends at the same time, or do they reach both ends at different time? Now, the answer to this question depends on where you're observing from. So inside the train, it's equal distance to both sides of the train. So your answer will be, oh, they should arrive at the same time. But if you're at the shore with the relative velocity to the train, because of how a velocity should add, this additive property of the velocity, you would say, well, the back end of the train should receive the light first, then the front end of the train, if the train is moving forward. And that's an interesting thing, right? Because now we don't have absolute truth anymore. When we're asking about the state of the universe, the question that we should be asking preceding that question is where you're observing from. What's your observer frame? So how is that applicable to distributed system? There's something called causal consistency, which is a kind of consistency that's not the blockchain's kind of consistency, but it's a consistency that is observer frame dependent, but still respects causal information. And I'll be covering causal information in the next slide. And here is a adapted diagram of the many consistency models and how they relate to one another. Jepson has this wonderful visualization of the many consistency models that exist for distributed systems. On the top, we have the blockchains model, which is kind of the dumbest, but also the simplest to understand and easy to work with kind of model, strict serializability. Again, that means that every happenings in the system can be ordered on the same timeline or total ordering, and that operations never overlap. So you would never start a transaction before finishing the preceding transaction. That is the basic model of how a programmable blockchain works. Now, if we can go down the tree and go to the causal consistency model, what we're basically saying is now we allow overlapping transactions to happen, and that gives us parallelism, right? That gives us the affordance that actors in a distributed system can make progress, mutating stuff and accessing stuff at the same time. They don't have to wait for one another to have non-overlap operations. And it turns out that causal consistency is the stronger kind of consistency that you can reach without having to coordinate. Coordinate basically is consensus, it's voting, it's the 99% of the block time, and so on and so forth. So if we don't want that, but we still want the strongest possible consistency model, then we stick to a causal consistency model. And causal information here, I think deserves some explanation. So causality is a funny business because what is cause and what is effect? Is it causation or is it correlation, right? This is the fundamental debate in physics and philosophy and so on. In distributed system, causality basically means that if something causally precedes something else, let's say A causally precedes B, we'll say that A could have caused B, or we can't really be sure. But just because of the structure of the time or structure of the ordering, we say A could have caused B because B was generated as an event with the knowledge of A, so A could have caused B. So that's basically in distributed system when we say causal orderings and causal dependency. So in a distributed system, let's say you and me are in a peer-to-peer network. If I generate event A and then event B myself, then I know for sure that B follows A. So this is the causal relation between A and B. And if my friend generates C, then D locally, then D follows C. But we can say A and C and B and D, these are parallel events. These are concurrent events. We will say they are causally independent, or they could not have caused one another because as these were generated, they were generated by independent processes without information traveling. So basically, the model that we work with is we allow parallelism, or we allow events to be causally independent to one another, and we do not force the total ordering on it. Unlike all blockchains, where basically through game theory and so on and so forth, a total ordering is forced on all the transactions that happen in the system, and there's all kinds of marketplaces that are trying to gain equilibrium where actors can make the most money by some kind of total ordering of events, and that gives us MVV and so on and so forth. So there's a lot of game theories going on, but the fundamental premise is that blockchains want to total order everything, and so there's a lot of funny business going into what is the total order of things, and we're saying we give up total ordering, we allow things to causally be independent to one another, but we still respect causal information, which means if I do something, then do something else, then I want everyone to acknowledge that the something else follows something. So the Holy Grail, I think, can be revised in the notion of causal consistency, which says, okay, we can have programs that are structured as BFT CRDT, and CRDTs respect causal consistency already. And these programs will preserve the kind of consistency that we like, And they interact via message passing. And that is another concept because if you want to have these users progressing at local speed, but if you require these objects or these programs to interact via context switching and blocking function calls, then they're strongly coupled again. You want things to go in parallel and loosely coupled. So then not only does these programs are being accessed concurrently by people, the interaction between these programs are also asynchronous in the form of message passing. And because we're decentralization maxi, because we love the idea of sovereignty and robustness and availability, and there's another latency problem that I'll be covering. So we want all these systems to run on top of a decentralized peer-to-peer network. That will give us the holy grail. So overview of the protocol stack. I think that the time doesn't permit to go over the entire stack, but what I'll be covering is the hash graph causal consistency layer. On top of that, I will be covering a little bit of live opting and CRDT layer. There is consensus layer on top of which there's how RAM operates. There's a lot of details going into that. I don't think I have time to go over, but we have an afternoon workshop that we can go over and we can go into details. So let's start with hash graph. So I think working with blockchains, we have heard about DAG-based blockchains, DAGs or directly acyclic graphs. There are blockchains that use the DAG as a structured data type to basically structure blocks instead of an unstructured mempool and everything goes into a single line. Hash graph is just a common data structure, right? So it's a DAG, and it's a self-certifying DAG because every link in this DAG is a hash. So for example, if you look at the E node, the E node contains in itself the hash of D and the hash of J. So then if the payload of E changes, or if anything changes of the upstream causal tree or the hashtag or the hash graph, the downstream node's hashes changes instantly. It's just like if you look at a block header that contains all the information of the previous blockchain, not contains, but contains the information, but not give you the raw availability of data. If anything in the history changes, the block header changes. The same idea with hash graph is that anything upstream changes, the downstream heads or downstream nodes would change. And so it's a self-certifying data structure. You can see it as blockchain is a single dimension data structure. And what we're saying is we want that multi-head writability. And therefore we explode the chain into a multi-head tree where people can write to the history at the same time. Okay, and these messages takes the typical structure of having a payload, and it has a set of causal dependencies that the message reports, so that E will report D and J as its causal dependency. It has a content addressable ID or CID. Basically, it's some kind of hashing of the entire message. And then there's a signature that identifies who, which user sent this message in the first place, identified by some public key. Okay, so this is the scenario where we have two players mutating same game world at 60 hertz each. This gives you 60 hertz input rate. So you can see that we have user A and B, and they're adding nodes to the same hash graph, and the circle nodes denote the heads or the latest nodes in the graph or the latest messages that have been written into the history. The rule of the game here is if I want to add a message to the graph, my new message needs to report all the current heads as my causal dependency. So I'm basically adding a new message with the knowledge of the current heads or the latest happenings in the system. And these graphs have wonderful reconciliation properties. So if you have two graphs and when you have users mutating their graph at the same time, these graphs differ. And when they exchange information, they will perform graph reconciliation, or they will try to synchronize on their graph, because the same graph gives you the same history, therefore gives you the same application state. So graph synchronization is key. Now, if these pointers are hashes, a message with unrecognized causality or unrecognized children nodes will never get reconciled. Because if you tell me something without explaining the causes of that something in my knowledge, then I will never acknowledge the information you give me. So if you want to tell me an effect, you also need to tell me the causes, and I need to understand the causes in my own understanding of the history. That will allow us to reconcile in a BFT way. So visiting actors trying to change the past or adding new information without recognizing old causes will never get recognized by the correct actors. This is the key to the BFT affordance. Now, this hash graph is a pretty general data structure. We can use this data structure to transport operations that are happening through a CRDT. So in the same way that you have, like in Cosmos, you have ABCI, which sort of abstracts away the consensus engine from the application smart contracts on top. The same way, we have a generalized data structure called hash graph underlying, and we have systems or protocols for these hash graphs to be reconciled and synchronized to one another. On top of which, we use this abstraction to transport CRDTs, and CRDT is the data type that gives us programmability. And we want to program things because autonomous worlds are decentralized programs at its essence. So hash graph transported CRDT, or in another word, Merkle CRDT, which was the name given by protocol lab researchers and higher network developers. The idea is that the payload of these hash graph nodes carry operations that are happening to a CRDT. So this hash graph gives you the operations happening to a two-phase set. A two-phase set is a CRDT that works like a mathematical set, but you can only add an element and then remove the same element, and the element cannot be re-added again. So every unique element has a two-phase sort of life cycle in this mathematical set. A refers to addition and R refers to removal. So just looking at this graph, you recognize that this represents the history of things that happen to a 2P set. If you traverse the graph, you can derive what's in the set at the end of the graph. So then we have live objects. So we want to conceive of alternative decentralized programs that's different from smart contracts, but still give us wonderful programmable capabilities. And there's a lot of language that goes into replicated objects, distributed objects, and so on and so forth. But a lot of these objects back in 1990s and early 2000s were basically server-based, right? So the idea is that over the web, you can have servers running object systems and exposing these objects for accessibility to other computers over the web. But these objects are hosted in a single server. Now we're running these objects replicated in a peer-to-peer network. So we're calling them live objects because they feel alive, they have low response time, and they're alive in the sense that their livelihood is autonomous because they're replicated over the peer-to-peer network. So no single person or entity can turn it down or can shut down or kill the object. So they're alive by default, and they should be persistent because of the peer-to-peer network robustness. So similar to how smart contract work, we think that a live object can be made of blueprint or classes. Blueprint is just a term we borrow from Unreal Engine terminology. So blueprints are, I think, a more familiar, friendly term than class to regular programmers or thinkers, creators of video games. With blueprint, you can specify how this live object works, the blueprint of an object. It is stateful, and the states are typed with CRDTs or other blueprints. So that basically means that you can compound or compose these CRDTs into larger, more expressive CRDTs. These CRDTs interact via signaling, and just like smart contracts interact via transacting against it. And there's an interface specifying the set of signals that a given live object handles or responds to. The handle function crucially needs to be monotonic function. So this is basically what the CRDT requires. So if you look into how state-based CRDT or operation-based CRDT works, it requires these mutator to be monotonic, which means the another term for that is inflation. If you look into the academics, inflation basically means that you are mutating a data structure without taking away information. You're always adding information to the data structure. And also there's a view function that gives you the state of the object. So it materializes as all the CRDT and gives you a single value representing its state. And finally, there's a merge function. So this is what makes live object different from smart contract. A merge function needs to be defined for each object so that these objects can be replicated to many people, and they have a way to use the same deterministic merge function so that they remain synchronized to the same object. And the merge function needs to be commutative. So there's some mathematical properties that need to be preserved with these functions. Signaling is the way these objects should be able to interact with one another. So here we have XYZ, or 3 hash graph representing 3 different objects. Signaling basically is one hash graph generating a message to another hash graph. And for trustlessness, we want the receiver side to be able to verify information on the sender side. So typically, like how IBC works, right? The receiver chain needs to be able to run light clients to verify information on the sender chain before accepting the message. So same work with live objects too, but now we're working with causal dependencies. Just to summarize, we think that live object gives us 3 affordances that makes it different from smart contracts. One is it's supposed to be running at 0 fee. And I think 0 fee is a strange idea because what if there's no cost to be paid? Can we just DOS the system, or can we basically tax the system without implications, right? There's like a nothing at stake problem and so on. I think the insight here is that because we don't run consensus, what makes blockchain expensive really is the consensus algorithm, whether it's basically having to stake CPU power or having to stake capital. And so users are paying fees for the opportunity cost of those capital investments of these validators running the network. But since we do not run consensus, we are giving interoperativity to peer-to-peer actors. One way to say this is it's basically low balance across peers. And so local users bear the computational costs of participating in an object or in a program. So if you bear the cost already in terms of computationally, then you don't need to pay the fee to some other validators or actors of the decentralized network. So that's the basic idea. The second affordance is log-free. Log-free basically just is derived from the idea that we don't run consensus for these objects to work consistently. There's no log, so everyone can progress at their own speed. A user might write to a collaborative document once per day. The other person might write to the document at 1 hertz. They can interact at different speed and not waiting for one another. And finally, loose coupling. We want these programs to be loosely coupled in the spirit of object-oriented programming that's originated by the Smalltalk or LNK, which means that if you want true encapsulation, objects should not be able to access actual function calls in internal structures of other objects. They should be passing messages, and how and when these messages are handled by objects is dependent on the object themselves, not by some underlying machines that schedule everything and so on. So we want true object-oriented programming model. Some examples include a multiplayer space. So this is the pseudocode of a multiplayer space included in the paper. The idea is that we can have multiple players basically changing their whereabouts of their avatars. And we want to have a way for these avatars to intersect and to be able to resolve their collision. Because what's fun without collision? And the funny business here is if both you and I can move at a local speed, then how do we resolve intersection? We can easily move into the same position, right? With an authoritative server, the server can decide who gets there first and reject the second person, or run some physics simulation to resolve that. But in a situation where everyone is progressing asynchronously, how do you resolve collision? One idea that we provided is that we can endow each rigid body or each avatar with a field. So the field basically is like a repulsion field that is larger than the boundary of your object, and that by detecting the intersection of these fields, we can have a commutative way of resolving or basically pushing them apart. But then the following question will be, well, what if they pass through or tunnel through one another before synchronizing the information? You have a tunneling. But because the hash graph records all the causal information, theoretically, it should be possible to traverse the graph to detect the tunneling and then have a way to resolve the tunneling. So I think long story short, there should be a rollback netcode implementable in the as a CRDT. And I think this is left as a programming exercise. I think this may not have ever been achieved before because in the history of CRDTs, collaborative documents, Figma or databases abstracting CRDTs is the major use case. We're now saying CRDTs should be able to make expressive video games. And so all the game physics and game programming exercises is transformed into CRDT programming exercises. Another example I think should be familiar is social graph. So Farcaster, a lot of us use Farcaster. Farcaster, apart from its blockchain component, runs a hub network that replicates a bunch of CRDTs. And these CRDT represents the mutations to the social graph, the open social graph on top of which like Broadcast Plan runs, for example. Some CRDTs include, you have a CRDT that represents people adding posts to it, another CRDT for people to remove posts, to follow people, to react to posts, and so on and so forth. And they have a hub network that replicates these CRDTs as a geo-distributed network. So the idea is that, okay, live objects should provide you the same affordance. You should be able to create your arbitrary social graph or relationship graph that's made up of CRDT at its substance and as a live object yourself. without having to run your own hub network or the entire forecaster machinery yourself. One final example that we offer is the possibility of a DEX. So it may be possible to construct a live object as a decentralized exchange that goes really fast. You have asynchronous users, in this example, posting orders, canceling orders, and taking orders asynchronously and exchanging information about the order history. And from time to time, this history should result in a bunch of trades that settle on a blockchain to actually change account balances. And there are notably security problems with this implementation. I think that's one of the open research problems, is that, okay, basically CRDTs, you can understand it as a multiplayer state channel, and like Lightning Network and state channels are supposed to take things at a very fast, to a next level of speed, by having blockchain accounts transfer or lock up some balances and allow peer-to-peer state channels to record transactions between peers and then settle the resulting balance back on chain. And we're saying CRDT may be a way to generalize a state channel to a multiplayer state channels that can always merge and become consistent to one another. So we imagine decentralized exchange possibly to be implemented as live object, but this is left as an open research problems. And I think once the protocol becomes available for testing, people passionate about DeFi will definitely try to adapt live objects for financial applications. So we're excited about the possibility. Now we move on to the random access memory idea. So what is a RAM, right? The RAM for the computer basically wanted to solve the problem of the main memory or the hard disk having a very long access time, and therefore a system is memory bound if the memory is slow but the computer is fast. So how do we resolve that? Well, we can have a memory hierarchy where you have a RAM in the middle that may be more expensive and maybe may hold less data, but it's faster and it's closer to the computer, so you have way less access time. For example, maybe one nanosecond as opposed to the main memory, which may work at, let's say, 1 millisecond. If you have a DRAM, it's probably even slower for older technologies. So maybe blockchains are hard disks now, and we're saying we can run a P2P network serving live objects, and this stateful P2P network is the RAM for the work computer, where the blockchains are hard disks. So this one mental model that we have, which is having a RAM network on top as a peer-to-peer network, serving these programmable live objects for applications to refer to. And these applications would also have ledgers and account balances and contracts on some blockchains that they like. And blockchains are hard disks, where the peer-to-peer network serving live objects are RAM. So the mental model, to go in a little bit, is we want to leverage growth in local compute, because I've played some of the cloud gaming, like GeForce has a cloud gaming platform. I used to play some other cloud gaming platform. There's always a problem with latency, or like streaming high resolution graphics, and the trade-off of not downloading a game client locally is the entire game experience becomes sensitive to network conditions, and that's not a very good idea for highly demanding game experiences. So the idea is that we recognize that internet improves actually slower than how our machinery improves in compute speed. So we want to put more compute locally, not remotely. And the problem with blockchain is because phone node is so demanding to run, right? Like multiple terabytes needed to run a phone node of a typical programmable blockchain. Regular users are not able to run full nodes. As a result, regular users rely on centralized gateways or remote machines to interact with blockchain. And so most users interact with the peer-to-peer network not as a peer-to-peer network. They interact with the peer-to-peer network still via client server gateway and possibly censored and possibly speed bumped access, a way of accessing. So if we want to have local speed, it's paramount that we allow users to run basically local nodes of this RAM network. So every user is participating directly in a RAM peer-to-peer network. That will give you local speed. And the implication of that is we need to tackle state expiry and succinctness from the get-go. We can't say that, well, blockchain state will grow indefinitely, but we'll kick the can down the road and think about state expiry and cleanups later. Because live objects grow so fast. Like imagine live objects where users are transacting at 60 hertz, and imagine 10 users. Then you would have a graph that grows at basically 600 nodes per second, and you can basically have a back of envelope estimation, the size of each message and how fast this graph grows. One thing that hindered CRDT practicality in the 2010s is because the metadata is so large, and the unbounded memory problem of having to maintain the entire history of CRDTs made it very impractical to run in a browser environment. So we need to tackle succinctness in compaction from the get-go. And also we imagine for a coherence problem, right? So for people that may be familiar with how RAM works, there's always a coherence algorithm that says, okay, CPU writes to a data that's available in the cache, but then that makes that data line or cache line different from the version in the main memory. So then at what condition do we update the main memory from the cache? And if we have multiple CPUs with multiple caches, and if there are mutations happening concurrently, then there should be a protocol that maintains a semblance of coherence among these cache lines. And that is a coherence protocol. So if we're running a RAP network for blockchain or IPFS as its main memory, then we need to derive a coherence protocol, when to update the main memory and when to synchronize caches and so on and so forth. Just a primer on compaction. What compaction means is throwing away causal information. So the idea is that in this diagram, if we assume that F and G are stable, meaning that no future events will have happened before them, then we consider them as stable. Once they're stable, their causal history can be compacted, because we don't necessarily need to remember all the causal history of these messages. We can compact A, B, C, D, E into a phi node that carries no payload, but it records a state, the state of the object. So this is similar to how, if we look into how the Mina blockchain works, for example, it basically snarkifies its blockchain itself, every block. So it keeps its blockchain very succinct. The same way, for live object or hash graph to be succinct is that we have a way to periodically compact these graphs to keep them small. One way to trustlessly compact this graph is following how Mina works. We can have a periodical compaction that is being recursively proved by some ZKVM. So the idea is that not only am I compacting my graph, I'm also proving that compaction was carried out correctly, and I'm also proving the verification of the previous proof of my previous time tick and pack it into the same proof for the next time. So then anyone accessing this live object can just pull the head of the graph, verify the proof, and understand that it's correct without having to traverse the entire history. Security problems. So there is a myriad of security problems. One problem is the problem of outdated messages. If we're, let's say you have a multiplayer game and some user has a horrible ping, and after some network delay, the players message everyone else saying that the player actually collided with everyone else at some past time, then maybe it's not desirable to roll back the game and resolve the collision and change all the downstream game states. So then I think it will be undesirable for applications to have to tolerate super outdated messages that may change their latest state. And so there needs to be a procedure of dealing with these outdated messages. But if we don't have the notion of time, if we have causal ordering, how should we determine outdated messages? Because outdated literally implies we need the notion of time to determine what's happened before and what's after. So then we basically conceived of the need to have a decentralized timestamping again, but just for outdating messages and just for other purposes, not for timing and ordering transaction, but for these additional facilities that may be required by the application. Another kind of attack is O-dependency attack. So we have established that if I want to run a hash graph of a live object, and if I want to perform a transaction or mutation of this object, my latest mutation should recognize the head of the graph or the latest information in the graph at its causal dependency. Now, I can do funny things by reporting bad dependency. I can say, I do this thing causally dependent on something that's a very long time ago, and therefore, this thing that I recently just performed appeared to be happening in the past or in the causal history. And this is a graph taken from the paper that says, if we have a decentralized exchange where it is sensitive who takes the order or who cancels the order first, O-dependency attack can be funny, because then the creator of an order can retroactively cancel the order once the creator saw which trader takes the order. So that can be a really funny business. And we have some ideas of how to tackle O-dependency attacks, but this remains an open research problem to be simulated and tested. Okay, so the mental model to offer at the end is that we basically imagine this to be a small talk system, right? So small talk system is a computer in itself that's fully object oriented. It not only consists of a bunch of class definitions of the object, it also consists of a bunch of stateful object with its state. And we run small talk system over a peer-to-peer network. And we imagine for future decentralized applications to have two backends. One is a smart contract backend, the other is a live object backend, because they have different affordances. And finally, we think that hyperstructure should be really made with smart contracts and live objects because they have different affordances. And together we can build bigger and more useful hyperstructures. Finally, the status of the project, we're prototyping the RAM network in both Go and Rust in this repo, open source repo. We're tackling various research problems in a transparent manner, so we have weekly calls that should be made public soon. And we're tackling problems with snapshotting, compaction graphs, coherence between the RAM and the main memory, IPFS, and consensus algorithm, and so on. And we're in the process of setting up a Berlin office to have a presence and to work there in person. We're looking for protocol research engineers, and we have some requirements listed. I will share the information later. And finally, we'll be hosting public dev calls and sharing more frequently in the form of blog posts very soon. Yeah, so the mission of this project basically is to advance our presence in cyberspace, to be in cyberspace together in a trustless manner. And this is the QR code for the Luma page for the meetup tonight. So the wine and food is on us for more discussions. Thank you.